Hello, let's do this question. So, is graph bipartite? You're given an undirected graph, and your input is basically an adjacency list. And you want to find out whether this graph can be made bipartite. That means you can partition it into two independent sets A and B, such that every edge is connecting a node from set A to set B, and vice versa. This also kind of implies that for each set, for your A and B sets, there cannot be two nodes in the same set that are connected to each other. So let's see if this is bipartite. Well, we can try and put 0 and 1 in different sets because there's an edge between them. They can't be in the same set. So they're in different sets, and 3 and 2 should be in different sets because there's an edge between them. Alright, so now we have all nodes in either set, but then we realize 0 and 3 are in the same set. If we put 0 and 3 in set A, and 1 and 2 would be in the same set. So, but there's an edge between them, so that's not bipartite. What about this one? Well, we can put 0 and 1 in different sets because there's an edge between them. And we could put 1 and 2 in different sets because there's an edge between them. So that kind of implies that 0 and 2 will be in the same set since there's only two sets. And then 3 and 2 will be in different sets because there's an edge between them. And that would mean that 3 and would be in the same set as 1. So then you have two sets. You have first set 0 and 2 and the other one with 3 and 1. And that works because nodes in the same set don't have any edges between them. So 0 and 2 aren't connected directly, and 1 and 3 aren't connected directly. Okay. So how do we find out how to do this? One way is to just do a DFS on the tree. So we go through and keep track of the depth, and if the depth is even, put it in one set. If it's odd, put it in another set. And if there's a conflict, then we know it can't be bipartite. So just to visualize this a bit better, let's say you have a node here. Node here, node here, and node here. We know the depths, but we take the depth modulus 2, so that will be 0, 1, 0, and so on. Let's actually draw some more nodes. And let's say there's actually a cycle here. Something like that. And this will be 0. To make it a little clearer, we can color in the ones that have a depth modulus 2 of 0. So this one. It's kind of like a graph coloring problem. So you can really kind of see that trees are bipartite because we can put these black nodes aren't connected to each other directly, and the white nodes aren't connected to each other directly. So we can put the black nodes in a single set and the white nodes in a single set, and that will be bipartite. One thing you notice is that this cycle here is how many nodes? It has 6 nodes, and that's one of the definitions of bipartite graph. If there are any cycles, all the cycles would have an even number of nodes. And it turns out that we actually don't need to actually do a DFS from this route. We can choose any. We can really choose. Maybe we can actually choose this route, and actually reroute the whole tree based on this node. And it'll still work. It will still be a tree. Well, it's not really a tree at this point because it's a cycle, but all the cycles are still have an even number of vertices, even because it doesn't matter which node we start at. We'll still, the black nodes still won't be connected to each other directly, and the white nodes are still separate from each other as well. And that's the idea. So we just do a DFS. But what if there are disjoint trees, or like disjoint graphs? So like maybe there's another graph here. So let's say that this is black, this, and we have another graph, say like this. This is black. Well, we can actually, it doesn't matter if we put this node, this white node, with the black nodes of this graph, and these black nodes with the white nodes of this graph. There's actually different possible partitions in this case. Both would work. So all we have to do is really keep a scene array, and as soon as we touch a node, part of a tree, we do a DFS, which would go through all the nodes in that graph that node is indirectly connected to, and all of these nodes would be in the scene array now. And then let's say we iterate through to the next node, and we find this one, for example. Since we've already seen it, it's already in the scene array, we can skip it. And eventually we'll get to one of these ones. And then we will do the same DFS, and eventually these nodes will be in the scene array. And we also split the nodes based on the color. And if there are any conflicts, we just set a global variable to be false, and that's what we return at the end. So by default it will be true, and then if there's any case where it fails, then we set it to false, and that's what the result will be. Cool, so let's give that a go. So we need to go through all the nodes in the graph, so we can set that I is equal to 0, and then I goes up to the size of the graph, and we do plus I. We know we need to do a DFS on the tree, but before we do that, we need to make sure we haven't seen it, just like we talked about. So if seen, if you've seen this, then continue. So we need a scene array. It's easiest if we can make it a bool actually. There are up to 100 nodes, and the nodes IDs are 0 indexed, so we can just say 100. We've used, let's say, static const int max n, so that's going to be 100. And we also need some other arrays. Let's call it BP for Bipartite. And there's going to be 2 of these, each with 100 nodes. And because these are declared as global variables, that actually initializes all the booleans to false, or just 0 equivalently. So we do a DFS. We have to define DFS. Void DFS, and we pass in node. Probably have to pass in the graph as well. Graph. What else? What else do we need? Ah, yes, the side it's on. That can be a boolean. Let's make an int. So here we pass in I, the graph, and the side. Let's just make it default of 0. And at the end, we want to return an answer, a global answer. Say answer is equal to bool's answer is equal to true initially. And at some point, if we find a case that that fails, then we set answer to false. Alright, so how do we do this DFS? So the main is bipartite function is done. How do we actually check if a case fails? Well, if we've seen a node before, we want to check that that node is in the right set. So if we've seen a node before and we say that the side is 0, but then we find that the side it's actually in is on side 1, then there's a conflict, and so that means we can set answer to false and return. Also, if like the answer is already false, then just return. Do an early return. Also, if seen, so if you've seen it before, if you've seen node n, you want to return as well, but before we do that, we want to check if it's on the right side. If it's on the right side, what happens? If it's on the right side, no, we want to check if it's on the wrong side. So which side are we on now? We want to check if side, so if the side we want it to be on, if it's not there, if this node is not on this side, then set the answer to false. Okay. Otherwise, we want to put it in a scene because we haven't seen it before. So scene of n should be equal to true, and then scene. Hold on. I'm going to put it on the current side, so BP side, n is equal to true. What else? I'm going to go through all the children of this node. Children would be auto. Let's see. Next, in graph of n, I'm going to do a DFS on the next, pass in the graph, and here we want to change, we just want to flip the side. So we could do that by just doing side XOR 1. Alternatively, you could do like side plus 1 modulus 2. It's the same thing. And yeah, that should do it. We could also do another earlier return here. So if we say if not answer, then break and just return it. Alright, let's see, side. Oh, so we have a default side, so we don't need that. Okay, that seems to work. Let's try another. This one should be true. This one is this case here. Okay. Alright, let's give that a go. Awesome. Awesome.